everyone, welcome to this video on the first lesson in the sound and light scheme. And I've called it sound and light because they are more concrete ways of thinking about the real topic of this scheme of work, which is waves. And this first lesson is one of our historical case study lessons. It covers different theories of light, so Newton versus Huygens essentially. And it's one of my absolute favourite lessons to teach, but I think any teacher would be forgiven for looking at the resources and looking at the kind of questions that we're asking and what needs to be explained and going, oh my goodness, why are we going into this? This is way beyond what we need to teach at Key Stage 3. And I think that's very understandable. If you were to kind of go on and do A-level physics, this would come up in year 13 in the AQA course anyway, in the turning points unit. So it feels like we're kind of pulling it down, and there are some things that you will have to gloss over in this lesson, but I think it's so worthwhile, and that's why I'm spending a bit of time at the start of this video explaining why I think it's worthwhile. And the reason is this. So when I was teaching in my first school, A-level physics, I was assigned the topic of waves. So I got to this topic and I was moaning in our kind of department room. Oh, waves. I hate waves. What an awful topic. And the reason I hated it was because it just felt so abstract. So we've all heard that classic question, when am I ever going to use this? Well, when you start getting onto waves and optics and all of the stuff that you end up doing at university and Fourier transforms and all of that stuff, it's just like, it just seems so kind of removed from anything that would ever be relevant to the way we usually interact with the world. But it was only, and this is a classic story, the more you teach, the more you read, the more you actually understand what you're teaching, the more you enjoy your subject. It was only after reading a lot that I realized that the reason we have to study waves is because the only way we can understand 20th century physics, and really I'm talking about quantum physics, is if we have a really deep understanding of waves and wave mechanics and so on, which comes into quantum physics. And actually, it was only then that I realized just how profound this topic is. And that's why I wanted to put something into this year 7 scheme of work, which just gives students a hint that there are some incredible big questions that physics is still grappling with, is still trying to answer. And so really what this lesson is about, it appears to be about light, but really it's an introduction to ideas around wave particle duality, and kind of the birth of quantum physics, which students will obviously study much later. And it's another chance to reinforce our guess-deduce check model. So what I would do to start teaching this lesson, apologies for that very long preamble, what I would do to start teaching this lesson is ask students what they think light is. And you'll get all sorts of answers. They'll probably tell you what light does. So it lights up the room and it allows you to see. They'll probably say something about energy without really being able to communicate exactly what they mean by that. And so you can introduce 2 really famous guesses. Now I tend to do it kind of vertically down the page when I'm teaching this. So I'm going to write guess in the margin over here on my page. And what I'll do, I'll write 2 different names. So we'll talk about Newton. Many of them will have heard of Newton from primary school and apples falling on his head and so on. They might not know that he was famous as well for thinking about light and so on. And I'm also going to write Huygens. And we're going to look at what these 2 thought about it. So Newton's guess was that light was made up of these tiny little particles called corpuscles. So I'm going to draw these particles kind of in a jet. And I like to explain this to year 7 students in a kind of simplified way. They're like little fireballs that come down from the sun and enter our eyes and somehow transfer energy to our eyes. And you can go into more depth if you wish. Newton imagined everything was made up of tiny little particles. This was part of the whole kind of mechanical philosophy that was around in the 1600s. So at that time, we assumed that we'd be able to explain everything in terms of matter and motion. So this was Newton's guess. Now, as we've looked at with Year 7 already, the way scientists generate knowledge is they make a guess about what's going on, and then they make deductions about what they would expect to happen. So the next thing we can write here is deduce. So we're going to say, okay, let's assume Newton's guess is true. Well, what would we expect to happen if? Now, I'm not going to do all of these in here, but I'm going to start with reflection. So if light was made up of these tiny particles, and then we shone light at some surface that I'm just going to sketch like that, well, what would we expect to happen? I might draw these along a ruler just so I get them in a straight line. So if I've got these particles all traveling towards this surface like that, and maybe I could show that light is coming in like that here. Well, what would I expect to happen if there were particles? You can ask students, or you can just tell them, well, you'd expect each of these particles would just bounce off, a bit like, I don't know, a ping pong ball or something like that. I'll try and get the angle the same, just so we don't violate the law of reflection. But what you'd expect is that they bounce off something like that. And, hey presto, Newton's guess that light is made up of these tiny little corpuscles agrees with what we observe when light reflects off a surface, because you'd expect them to kind of come in at one angle and bounce off at the same angle. We're not going to go into conservation of momentum and all that stuff, but basically that's what you'd expect to happen. So we can show students, well, okay, according to this deduction, so far, Newton's guess is probably true. Now, at this point, we can maybe introduce Huygens' guess. So Huygens said, well, I'm not sure about this whole particles thing. Where are these little fireballs? Why is it that we've never managed to detect these tiny little particles? He thought, and you know, you can tell a story here. I think it was Dutch, if I remember rightly, Dutch or Danish, but somewhere in the North Sea. And you can imagine him sitting at the harbour wall and watching the waves kind of come in against the harbour wall. And he said, well, hang on, I actually think light is made up of waves, a bit like the waves that you see in the North Sea. So his guess was that light is a wave. And he said, well, okay, let's think about reflection. And again, we're introducing new words to students. We don't mind at this stage that, you know, I mean, I hope they've heard of reflection. They probably have, but if not, it doesn't really matter. They don't need to understand everything. We're just trying to give them a picture of how all of this fits together. And what you can do here is show, well, okay, if I'm looking at the harbour wall from above, what I'm going to see is the waves coming in like this. So this is an opportunity to start by drawing some wave front diagrams. These sorts of things like this. And you might even want to find a picture of this happening on the internet. But if this was to happen, oops, then what would happen is this, is that these waves would actually bounce off and look something like this. Now I need to not draw a right angle. It might be easier to draw a kind of ray coming in like this so you can get the angle right. But what would happen is they would bounce out at about the same angle. And this is a bit of a complicated diagram, I accept. But what would happen is these waves would bounce off like this. And again, rather than draw it, you might want to just find a picture on the internet, because you will see there are pictures to be found of water waves reflecting. But what you would see here, my diagram's not the best here, but hopefully this makes sense. What you would see is that the water waves reflect at the same angle as well. So this is what we'd expect to happen if light was a wave, that it would come in at the surface and then bounce off at the same angle. Again, my diagram's not great there, but that's one that you can practice. And again, a video might show that better. But the point that we're trying to make to students is, well, actually, either of these guesses could be correct. If we just take reflection as the thing that we're trying to explain, both the particle theory of Newton and the wave theory of Huygens would explain reflection. Now, in the questions and so on, there's something about refraction. You can draw those out if you want. You might want to just find some sort of video or diagrams or whatever. I'm not going to do refraction here, just for the sake of time. But you can draw the same sort of thing. When you get to year 13, actually, you realise Newton's theory makes a theory about, it kind of assumes that the particles would speed up when they get into the more optically dense medium, like glass from air. Whereas Huygens' theory argues that they slow down, and actually that's another reason why eventually people decided Huygens was correct. Sorry, that's a bit of a spoiler alert. But the one that I think is really great, and students absolutely love this, it's really, really nice, is diffraction. And again, you might think, hang on, you've not taught anything about waves, and you're going to start talking to them about diffraction. But that's kind of okay. And if you just go with it and talk them through this, again, we're not asking them, we don't want them by the end of this lesson to have a really deep understanding of diffraction and be able to predict lots of different things. What we want is to give them a sense that there are these really confusing, counterintuitive phenomena that science has scientific theories like Huygens wave theory has managed to explain. So what we're going to look at is double slit diffraction. And if you're not familiar with this, then hopefully this will make it a bit clearer. What we want to do is imagine that we're going to shine light at two very tiny slits that are close to one another. And you might even want to make them even closer than this. But I'll leave it for now because it's kind of fine. So you want to ask students, well, okay, if light is made up of these tiny particles, I'll just leave those here. What would you expect to happen when you shine light at these two slits very close together? In fact, I'm going to make those even closer together because it's kind of what you need for double slit diffraction to work. So let's just rub that out. And let's make those even closer. So we've got a tiny little kind of gap there and two slits like this, okay? You might want to draw something like that just to show what we're talking about. Now, if light was a particle, what you'd expect to happen is that light, as it comes towards here, it's either going to go through one or the other slit. And again, you could sort of say, well, look, a beam of light is not perfectly infinitesimally small, so you're going to have lots of particles coming all that way towards the slit. Essentially, what you'd expect to happen is light either goes through, or these corpuscles, these particles of light, either go through one slit or the other. So if you were to put a screen behind these two slits, well, what would you expect to see? You'd expect to see these two kind of bright spots where light is landing, like that, and then the rest of it would be dark. So I'll shade this in like that. It's a bit awkward to draw, but hopefully you can see. And you might want to label that as two bright spots. That's what you'd expect if light was a particle. And this is where it's interesting because actually you realise this is much more intuitive. Newton's particle theory, that's much easier to get your head around because you kind of would expect, okay, if you've got two little slits here, you'd expect to see two bright spots over here. Because imagine if you did it with a torch, that's what you'd see. You'd see two bright spots and then the rest would be shadow. Now, at this point, you can say, well, okay, is this what happens? And there's a great video, I think it's Veritasium, you can look it up, Veritasium double slit experiment, where a guy, I think in Australia, shows a load of people this, and he kind of asks them the same question, what would you expect to happen? They say, oh, two bright spots, and the rest would be dark. And then they look, and actually you can see inside, what you get is this crazy colourful pattern that is not what you'd expect at all. Now again, you're going to talk through this in terms of the wave theory. It's going to go a bit over students' heads, but you can just kind of tell them to trust you on this for the time being, is that the only way you could get that pattern that you actually see, which is like this, and it's kind of a bright spot in the middle, and then lots of smaller bright spots kind of evenly spaced on the outside, and then dark patches in between like this. You also get some kind of rainbow colours when you do it with white light because different wavelengths of light diffract differently, but again, it doesn't really matter too much. I just realised my picture is in the way there. The only way you could explain that is with the wave theory of light. And again, the reason that video is really nice is because, I need to get that in the middle. Oops, let's just do it like that. Is because he shows it with water waves and he shows kind of what's going on. So it's a really nice illustration of it. But the only way you can really explain it is by this kind of pattern like that. And again, maybe even rather than doing it like that, we could do the wavefronts type of diagram and show what's going on. So you might want to do it like this. that you get these kind of, this sort of pattern from each slit, but then they start to interact with one another. And again, my diagram is now really messy. But the point is, and again, if you watch that Veritasium video, this is where visualizer diagrams aren't the best. Actually, sometimes videos could be really helpful. But what you get is this pattern of bright and dark fringes, which is characteristic of waves. So you might say something here like bright and dark fringes. And again, the visualizer is hard to represent some of these phenomena. That's why video in this case is really, really good. And what's the point? Why have we gone through all this with Year 7 students? Again, what this is when we actually check here, I'm going to write check down at the bottom like this. When we actually check here, when we checked with the phenomenon of reflection, the particle theory seemed to do a pretty good job, as did the wave theory. Both of them could explain what is actually observed. And the same with refraction as well. Both of them, at a superficial level, can kind of explain what's observed. But this is where it gets really cool, is you can say to students, but if you do this and you shine light at these two little slits, when we actually check, well, we'd expect this to happen if light was a particle. We'd expect this to happen if light was a wave. Which one of these does happen? It's not this one. This one does not happen. This is the one that happens. And this is why Huygens' theory, that light was made up of these tiny waves, was the one that ended up being believed. That's what we now think to be true, or at least that's what we thought to be true in the early 1800s, after Young had shown this effect with two very tiny slits. But then that's not the end, and this is where it gets really, really interesting. And again, you may have to do some reading on this, because it goes a little bit beyond what most people have studied in physics. Where it gets really interesting is, if you then fast forward 200 years from this experiment being carried out and get to Einstein in 1905, what he showed was that actually light is kind of both. Sometimes light behaves like particles, sometimes light behaves like waves. And this is really, really mind-blowing to students, is that actually we can't be sure. And they're used to hearing about science as this kind of body of really well-categorized facts, boom, 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 boom. They just need to commit them to their long-term memory. But actually, you can say to them, there are these huge open questions that science hasn't really come up with simple, satisfactory answers to yet. And this goes much broader into physics, about how physics, it hoped to have this perfect mechanical explanation of the world. And we were really confident that we'd managed to explain everything in the 1800s, and then in the 20th century, in the 1900s, that whole confidence broke down. And again, this is where I would say, show them some videos, maybe stuff about quantum physics, Dr. Quantum videos, or I'm sure you've got others that you can show them. Show them some of this cool stuff, because this is what's going to give them that inspiration to study it a bit more. And again, if I go back to my experience as a Year 12 teacher in my first school, I was bored of teaching waves because I didn't see why anyone would want to study it. So think about what it must be like if you're a Year 7 student studying waves. I mean, super, super boring. But if you give them a sense that it's only by understanding these really subtle, difficult, but profound ideas that they can get onto this whole other world that science has kind of created, that's going to make this topic a lot more interesting. So we've looked at what is light in this lesson, and we've tried to introduce the kind of reason that we might need to look a bit more into the wave theory. What we do in the next lesson, which is called What is a Wave, is we look in a bit more detail. Okay, light is a wave, but what do we actually mean by that? And what we're going to see is that the early theories of light, and that's what we're going to talk about mostly in Year 7, they thought of light as a mechanical wave, a bit like water waves or something like that. It's only much later that we're going to get onto this idea of electromagnetic waves, which they're then going to take forward into GCSE. But first, we're going to start with mechanical waves and give them a sense of how light would operate if that theory was true. So that will be the next video. Thank you.